what a dot product was, and then we learned what you could do with dot products. Dot product is the type of thing that came up so often that a special name was given to it. It was a structure that was noticed in many different places, so they said, let's call this dot product so that we can just call it a name. We give it a name because it repeats itself all over the place. Kind of like in the quadratic equation. What's the thing under the radical called, under the square root? Do you remember what it's called? The discriminant. It's called the discriminant. But yeah, it's called b squared minus 4ac. That's correct. It's called the discriminant. You can do something with the discriminant. You can tell how many and what type of solutions a quadratic equation has. There's another term we need to talk about. It's called the gradient vector. So yesterday, this is important. A couple days ago, actually, not yesterday. We talked about how the directional derivative could be computed like this. Do you remember this right here? This was yesterday or 2 days ago, right here. This. See this right here? Remember that? We worked through the logic of why that's true. So if you want to find the rate of change in a certain direction, it has to be a, you turn it into a unit vector, and then what do? You find the partial derivative with respect to x at the point, and you multiply it by the ith component, and then what do you add it to? The partial derivative with respect to y evaluated at the point times the jth component, right? We did that before. This is the sum of the product of two things. This is the sum of the product of two things. So what's another way to write the sum of the product of two things? The dot product of two things. You can write it as the dot product of two things. All this is a mechanism. Look, if these are two vectors, and this is kind of like the long way to write the vector. I generally don't like writing the i's and the pluses. I like writing it as like two vectors like this. You take this and you multiply it times that. Then you take this and you multiply it times that. And you add them together.
That's the same thing.
This is the definition of what dot product means. When you take the dot product of 3 and 2 and you dot it by, the dot product of 3, 2, and how about negative 2 and 3, what's that dot product? That's 3 times negative 2 plus what? 2 times 3, and what is that? 0. Well, the dot product is a scalar. It happens to be 0. What's a cool conclusion you can draw about these two vectors? They are what? They're perpendicular. Nice. Okay. All this is, first of all, is we're naming something and disassembling it with the dot product. We're not doing anything with the gradient vector yet. So the question is, which one is the gradient vector? This is the gradient vector right here. This is the gradient vector right there. This is the gradient vector right there. So what's the point? Well, if that's the gradient vector, the first point is you get to write this, grad FAB. What does that mean? It means this. Mathematicians love to write things in shorthand. We love to come up with variable names for things. If something gets repeated a lot, instead of writing out the whole word, we come up with some Greek symbol and say it's that word, right? Like, for all, there exists, unique. Those are all single syllable representations of words. Are you with me so far? Okay, so this is what we have so far. The directional derivative and the gradient. If f is differentiable at ab and u equal, okay, so they're just setting you up here. This is what I had above, except what are we calling this vector right here? We're calling it the what? The grad, the gradient of f, the function f. We're calling it that. So mathematicians love to just write things shorter. So now this is how we're going to write the directional derivative. The gradient fab dot u. U is the what? The unit vector going in the direction you want to go in. And the grad AB, what is that? Partial with respect to x at the point, comma, partial with respect to y at that point. Exactly, right. So if we want to find the gradient vector, fx, xy. What's fx, xy on this one?
1 plus 1.
E. Haha. What about fy, xy? What's that going to be?
Y.
No, careful.
Y.
Just e to the y. It's just e to the y. Oh, okay. So what's fx at our point? 1, 1.
1.
Yeah, it's always going to be 1. What's fy at 1, 1? E. So what is the gradient? So the grad f at 1, 1 is what? 1, 1. What's another way to write that? 1e. Sorry, I can't write. Sorry, excuse me. You're like, that is not right. 1e. That's another way to read 1i plus ej. Yeah, you can write it either way. I personally, this is my preference. I like writing vectors like that. That's just my preference. It's easier for me to see. So that's the gradient vector. Now, if you have the gradient vector, how do you use that to find the directional derivative in any direction? You just dot it by the unit vector. That's it.
By its own unit.
No, by the unit vector that in the direction you want to go in. This is the gradient at that point for that surface. That surface is bubbling like this. There's a specific point on the surface, and here's the gradient vector, okay? I could be heading in any direction I want to head in. I hit it that way, right? How do you find the rate of change in this direction? You dot this vector, the gradient vector, by the direction you want to go in. This is the short way, the shortest way there is to do these directional derivatives. So I could then say, we could pick a direction, right? What direction? Pick a direction. Give me any vector you want. Any vector you want. V is what? Give me any. 3, 4. Okay. V is 3, 4. What's the first thing we have to do to this vector? What's u going to be? V over the magnitude of v. So what's our coefficient out front going to have to be? Yeah. 1 over. Yeah, you're right. You're 3/5 times 3, 4, right? I'm just factoring it out.
Yeah.
You could put it in, right? So if we wanted to know what is f in the u direction, what's that going to be? Oh, it's 1/5. Why 3? Yeah.
No, I was gonna say.
Yeah, you said the first one, and I stopped you. My fault. Thank you, Michael. So if we want to actually find f in the u direction, the rate of change in the u direction, what's it going to be? 1e dot what? 3 over 5, comma, 4 over 5. That's it. And then you just do the math. What's it going to be? 3/5 plus 4e over. There it is. You just figured it out.
3 plus 4 equals 5.
That's it. That's it. Okay, so here's the big idea, though, and this is the huge thing that you really have to focus on. This is a little, seems a little weird, but I hope at the end of this it'll pop in your head and you'll be like, oh, okay, I kind of get it. So first of all, you have a surface that's bubbling, right? Whatever, it can be any surface you want. We're dealing with continuous, but it's a continuous surface, differentiable. The gradient vector at any given point is going to be a vector. You with me so far? Okay. So here's the point we're at, and here's the gradient vector. Do you understand how to find the gradient vector? Go like this. Yeah, you do. Yeah. Don't tell me what I understand and what I don't understand. Okay. At that point, you could start walking in any direction. So this u vector could go in any direction. Are you with me so far? Okay. So fu, which is a fun thing I get to say now in class, is, what did we just say this is? It's the gradient vector, grad f dot u. Hey, let me write it even shorter. Okay? Are you with me so far? This is a restatement of what I just said. This is not new right here. There were 2 definitions for dot product, algebraic and geometric. We called it True, it's like, can you name the person who invented this microcathode in 1957? Someone who has never been in my kitchen. That's true, but it's not the answer I'm looking for, okay? That's a Cheers joke, it's not mine. This is the geometric definition, right? 2 vectors dotted together. It's the magnitude of the first times the magnitude of the second times what? Cosine of the angle between. You with me so far? What's the magnitude of u? 1. So what have we just figured out? Fu is equal to the magnitude of the gradient vector times what? Cosine. Okay, let's look at this right here. This is a scalar, right? Scalar. What is the largest value cosine can be? 1. When? When theta is 0. Okay. Yes, or infinity times and blah, 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 and bleh, 0. Just go with 0. But it's always 0. Or 360 or 2 pi. Great. Okay. What does it mean if theta is 0? The angle between them is what? 0. So that means the gradient vector and u are pointing in the
same direction.
So that means this is maximized when you're going in what direction?
The same unit vector.
Well, it doesn't have to be unit. Direction. We only care about the direction when you're going in the direction of the gradient. The gradient points in the direction of the greatest rate of change. You can find the gradient in the look, ready? Do you understand this?
Yes.
Oh, so okay. Oh.
Do you understand this? Yeah. When is this biggest? When theta is 0, right? But if theta is 0, what's the angle between you and the gradient?
Non-existent.
So they're pointing in the,
Same direction.
so the gradient vector automatically points in the direction of the greatest rate of change.
Wait, so that.
So if you're standing on a surface, let's say you had a function for this mountain you were on, and you wanted to know what direction do I go in to go on the steepest rate of change?
So is that the point of gradient vector?
One of the big points. It's one of the huge points. One of the huge points of gradient vectors is we now know the direction to go in the steepest. Let's look at the opposite. Cosine is minimized when, what's the smallest number?
-1.
When theta is
Negative.
pi.
Or pi.
180, right? So what direction are we? Oh, look, 180, opposite direction. Steepest, direction of the gradient. Steepest could also mean steep downhill or uphill, right? You have to be careful. Key thing is this line. Make sure you understand this. Make sure you understand that. That's key. But look what they have here. The max. Oh man, I gotta watch out for my thumb here. Here's the max. Here's the min, and it's 0 in the other directions. Why is it 0 in those directions?
Because this one is pi over 2 minus 0.
Right? It's really cool. Okay, so what does this mean visually? It means this.
Like, is it like
Right? Let me draw a picture and see if you can get it here. So let's say I had contours that look like this, okay? Let's say this was 10 and this was 11 and this was 12. Let's say I was at this point right there. I'm standing on that point right there. Can someone describe for me what direction the gradient vector is going to go in? How would you describe how to draw it? Is it going to go like this? No. What's it going to do? So is it going to go like this? No. Where's it going to go? What'd you say? Perpendicular. It's going to point in the shortest path to the next contour line. That right there is the direction of the grad f. Yeah. So what does it tell you? So this right here, if this is 90 degrees, what's the rate of change if you're tangent to this contour? Assuming that that's 0. Largest, 0, 0, smallest. The steepest rate of change. When you look at a contour diagram, when you look at a topographical map, everybody, you're like this, you're like this. What happens if you get a bunch of lines that are really close together? What does that mean? It's a cliff, right? It's like a big hill. Go back over here. What's the steepest path from this point? Well, it's not like this. It's the shortest when you're looking above. The gradient vector is going to point directly at the next contour line.
Wait, okay.
Because this is the steepest path. If this is 10 and this is 11 and this is 12, the steepest path is pointing straight at the next contour line. Straight at it. 0 for rate of change here, largest, smallest, 0 going the other way. So what kind